Hello, everybody, and welcome back to Better Brainwaves. If this is your first time coming to the YouTube channel, welcome. If you're a regular follower, subscriber, welcome back. This is going to start our four-part series on laser application. So we're going to talk about all the different types of low-level light therapy, which includes diodes and includes lasers and all the complicated and complex issues surrounding the laser, things you might want to look out for, and some tips on how to apply the laser, how to buy one, what to look for. So we're going to cover, it's going to be a pretty comprehensive series on laser. So I hope you enjoy the information. If you do, please press the subscribe button and the like button, and that allows us to get out to more people, because we want this information to get out. And I know it's fairly a complicated issue with laser. And as we start getting into it, you'll see that it is it's really worthwhile getting some information, having some research done. Now, I've also just done a second podcast with Alex Fergus, and I will post his podcast site or his YouTube site in this video, so that you can know where to go and go see that interview. We cover a lot of stuff in that interview, and I think it would be a great addition to this series for you to learn about laser and what it can do and how it can help you, and maybe things to look out for so that you don't hurt yourself. Okay, so without further ado, we will start getting right into it. I'm going to be in the top right-hand corner, just like that. Hi, everybody. So first of all, we always want to start at the beginning. What actually is laser? So laser is basically an acronym for light amplification by stimulated emission of radiation. Light amplification by stimulated emission of radiation. That sounds pretty complicated. So basically, laser has special qualities that normal light doesn't have. And some of those special qualities are that there's a high degree of spatial coherence, and we'll talk about what that means in a minute, and a high degree of temporal coherence. So over time it stays the same, and the output of the laser signal is very coherent. So it's limited distraction or diffraction, and you can have very low divergence and concentrate a beam over large distances with laser. And so the laser we're going to use is not going to be going over large distances. It's probably only going to be going maybe, 6 to 8 inches, something like that. 100 millimeters, 100 centimeters, 10 centimeters. You're not going to get all going, this laser that we're using going a long way, because most of the time it will be in contact with your skin or some kind of body part. So let's talk a little bit about what is the difference between ordinary light and laser light. So you go out into the sunshine, you're going to get some light. So how is that different from the laser? Well, basically, laser is monochromatic. So it is usually limited to one or a very narrow range of wavelengths. Most of the time, one wavelength. And ordinary light is a number of different wavelengths, which gives us the rainbow effect of colors, because the different wavelengths of light, including laser, will have different colors associated with them. Now, it's also collimated, so it's a narrow beam, whereas normal light radiates in all directions. Now the coherence is interesting. So this is demonstrating a coherent wave. So there's two waves here, and both of them are quite close to each other. And when that closeness approaches singularity, or approaches being the same, then we call that coherent. So over here, where the sunlight is, where ordinary light, you see it's not coherent, it's incoherent, it's all over the place. And so these different properties of laser are things that we can use to help us do different things in our body. So more differences, again, we're just going to continue to sort of drive this home, because we have monochronicity against polychromatic, or the ability to produce a bunch of different colors or a bunch of different wavelengths. Coherence, where the waves are the same. Incoherent, where they're all over the place. Collimated and divergent. So these are the differences that I've sort of gone over before, but I thought this picture described them a little more clear. So I thought I'd take you through this one too. So those, excuse me, those are the differences between laser light and non-laser light, like might be produced by a flashlight. Now, a lot of the questions and a lot of the effects of low-level light therapy depend upon how the light is produced. So we now have LEDs and we have laser. And a lot of the times people are asking me, well, what's the difference between a laser and an LED? And basically a laser emits light as a result of photons striking an atom, and that atom is compelled to release a similar photon. So basically, this is why we call it stimulated emission, because the emission is stimulated by photons striking an atom. So when the photon strikes the atom, every time the photon strikes, even a new photon strikes the atom, a similar photon will be released, and that's why the beam of light produced is coherent. So the light emitted by an LED consists of many different colors, while the light generated by a laser is monochromatic. Okay, so a single color is generated. Now, I'm going to show you another picture here that shows an LED. So the LED is incoherent. So it's making light that is emitted by a consequence of charge carriers recombining across a P and N layer. And the P and N layer are these, the P layer is here, the N layer is here, and when we have basically these two plates put together, we get an active generation when we pass a current through here to generate light. But the light, you'll see, goes in different directions, so it's not coherent. Okay, now I've got another picture here that shows this. So here's sunlight, so this is incoherent. Here's laser, which is very coherent beam. And then here's light emitting electrodes, which are almost the same, but they are now not coherent because they have shifted. So there's a phase shift in the light emitting diode. And we'll talk a bit more about the differences between the effect that diodes, so LEDs, have, and the effect that laser has on biological tissue. Both have an effect, but there's some research coming out that's showing laser is more effective. Now, we have different types of light have different types of penetration. So we need to start investigating this, and we'll get into this in more detail in future episodes. But basically we have the red spectrum of light, which is the least penetration. And then we have the infrared spectrum of light, which penetrates a little bit deeper. And then we have the infrared laser, which penetrates the deepest. Now, all of these things will depend upon the type of tissue that we're penetrating, the wavelength of the light that's being used, and the intensity of the light that's being used. And all of these factors will combine together to give us the actual energy that is arriving at our target tissue, which in this case might be bone, for instance. Okay, so we're going to talk about the intertwining of these things and how they all sort of relate in future episodes. Now, we also have other factors that can affect the amount of energy that is reaching the target area of the tissue we want. So when we have, and this is just talking about the wavelengths generally, and whether we pulse the laser in short pulses or long pulses or no pulses, basically. So here we have showing that when we have a short wavelength and when we have, so the short wavelengths don't penetrate as far as the long wavelengths in most cases. Okay, and if we have a short pulse or pulsing of the laser turning off, turning on, turning off, turning on, and the time in between those is short, we get a less penetration than if we have a long pulse. Now that we can extrapolate out, and we can say if we have no pulse, so a continuous laser, it's actually going to, most of the time, have a more penetration depth than a pulse laser. Now, this is also starting to get into how different types of tissues respond or absorb, reflect, all the different stuff that happens. So to light before it actually can get to the place where we want it to get to. So white matter, for instance, in the brain, white matter is composed of axons and pathways. So they're forming connective pathways between different areas of the brain. And they're highly, the myelin in these axons has a high fat content. And so the fat absorbs the light rather quickly and rather more ferociously than does things that are not fat. So the gray matter, which is the actual neurons, don't have a lot of fat. They have some, but they don't have a lot. And so penetration can happen in that gray matter deeper than it can in the white matter. Now, all these things can be compensated by adding more power, more intensity to the beam, and changing the wavelengths of the beams used. Now, I just wanted to quickly go into the classification of lasers, because when some people hear lasers, they think of, oh, the lasers that you use to cut steel, or the laser that you use to cauterize wounds in a surgical procedure, that type of thing. So we classify these things, and the classification that's generally recognized across the world is the International Engineering Consortium, who've come up with these standards. And so class 1 is kind of the laser that would be in a CD player. Class 2, laser pointer that you use. Class 3 is most of the time where our low-level light therapy will lie, okay? And then class 4 are more powerful lasers, which you can use in surgery. So to cauterize wounds. So we're usually looking at a class 2 or 3 laser that we're using for low-level light therapy. Now, low-level light therapy has a specific definition, and basically it's red or near red in the spectrum, and that spectrum ranges roughly between 600 and 1,000 nanometers. Now, what we're describing, the 600 to 1,000 nanometers, is a wavelength, and so we can make lasers basically of any wavelength. Okay, but if they want to qualify as low-level light therapy, they have to be between 600 and 1,000. Now, sometimes we go outside that that range a bit. Maybe we might be up to 1,080 or 1,060, but it's roughly around that range, between 600 and 1,000 nanometers. And then it's also important, we need a power density at the surface between 1 watt and 5 watts per centimeter squared. Excuse me. Now, low-level therapy or cold laser is the type of light that has energy densities that are low, as we just explained. Class 3 laser usually, and they don't produce a lot of heat, but they can produce heat. I mean, if you have a laser with enough intensity at a high enough wavelength, you can create burns both on the skin and maybe even subdural burns. So we need to keep that in mind. We need to be cognizant that we're not creating any kind of burns in the tissue. And most of the effect of the low-level light therapy is photochemical. So in other words, it's caused by the light changing chemistry inside our body. It is not related to the heat that's produced by the laser. Okay, so that you wouldn't really want to use a laser to produce heat. For instance, if you wanted to have heat go through a joint, that's probably not the most efficient way to do it. There's other better ways. So the laser works, especially when low-level light lasers work by the light causes a change in certain parts of cells, which then cause changes in the way chemistry is happening inside those cells. So that's why we call it photochemical effect. Okay, so that's another important thing to remember. Now, how does the laser actually work? How does it cause a biological effect? Why would this shining light on my skin change the way my chemistry works in different cells in the body? Or shining it on my head, how does that change the way the neurons work inside the brain? Well, basically, again, we're just emphasizing that low-level light therapy has no or very little thermal interaction. Stating again, you can buy lasers, on the market that say they're low-level light therapy, but they can still create a sufficient heat to burn people. Okay, so we just got to remember that. Now, basically, we want the laser for the photochemical effect. So we get biological effects from this photochemical activation, which changes activity in the cells and tissues. Now, basically, there's a type of receptor in our cells, and so in the organelles of our cells, and these specific organelles are called mitochondria, and they have receptors that are sensitive to light, and these are called chromophores. Okay, so when a chromophore, which is a molecule inside an organelle gets struck by light, there's a change in the way it performs its chemical functions. Okay, now some of these, what is a chromophore? Why would we have these? Well, chromophores are compounds that probably we have carried over in our evolution from when we were in the sea or when we were dependent upon sunlight to produce energy. And they have carried over in us through evolution for some reason that we can speculate on what that reason is, but the point is they are there. So these are the compounds that we usually consider to be chromophores, things like chlorophyll. So we know that the plant gets the energy from the sun, it produces carbohydrates so that we can use it. Hemoglobin. So this may be new to you, but hemoglobin has the ability to alter its activity if light shines on it. Myoglobin, which is another protein that's in a muscle. Cytochrome oxidase, which is really the big one that a lot of the effects that we're going to see are going to be coming from. Other cytochromes besides cytochrome oxidase, flavin and flavoproteins and polyphorins and profrins. Now, all of these things, some of them have not been investigated very well. And we don't know a lot about them, but we do know they do change the chemical activity when they absorb light. Okay, now we're starting to understand a lot about cytochrome C oxidase and the other cytochromes that are in the mitochondria. So let's look into that. We'll see what we know about that. So basically, neuromodulatory effects of red and near-red infrared wavelengths, and we'll talk about those in a second, have a variety of actions that can be beneficial. So we have different categories of how light coming in from 600 to 900 or 600 to 1,000 nanometers can change through these chromophores, photoreceptors inside the cell, change the cell's activity to produce better wound healing, tissue repair, sometimes tissue death, and tissue death prevention. Okay, so there's a very fine line between too much activation and not enough activation. Too much activation can be cytotoxic to cells, so we'll get into that a little bit in further episodes. We can reduce inflammation, we can reduce pain relief, we can reduce edema, all the chronic type diseases that may tend to happen. Neurogenic pain, we can reduce the neurogenic pain, and we can reduce neurological problems, that type of thing. Now, basically what happens in a very simple way is that the photons, remember we talked about photons and how in a laser the photons are coherent. And so they're coming, the same photon, basically at the same speed, is arriving and they're triggering these signaling pathways. And the photon basically is absorbed by the chromophore. And some, basically, electrons become excited and they jump from low energy orbits to high energy orbits. And with this energy release, the system can use that energy to do things. And most of the time in chemical reactions and things like that. So what we're really looking at here is the movement of electrons in the atom from a low state of energy to a higher state of energy, and then sometimes they will return back. Next photon hits, up it goes again. So this is in physics, this is a well-known phenomena that has been studied for years. And so there's not much controversy around this. But we're just trying to give you a basic understanding of how this light coming in can produce chemical changes in the body. Okay? Now, we talked about this thing called the mitochondria. And the mitochondria is an organelle that basically is in pretty much all our cells. And it produces, well, it does a lot of things, but one of the main things is it produces ATP. So ATP, adenosine triphosphate, is the component or the molecule that pretty much all of our biochemistry is driven by. So it's kind of like the power that drives all of our chemical reactions. And so when ATP is abundant, we can have a lot of things happening. If ATP concentration goes down, then we're limited to what we can do because we don't have enough energy to power all of the activities that potentially we want to do. Now, basically, cytochrome oxidase, which is an enzyme that's inside this mitochondria, is one of the primary photo acceptors of the light in the frequency range that we're talking about, or in the wavelengths that we're talking about. It's also the enzyme that's responsible for catalyzing oxygen consumption in cellular respiration. Okay, so it's allowing things to be oxidized in our chain of energy production, which is known basically as glycolysis, and then through the Krebs cycle to produce the ATP that we need to burn or activate things inside our body. It's also, interestingly enough, it's also responsible for the production of nitric oxide. And nitric oxide is very important in allowing blood vessels to dilate. So that's one of the things that it does. And so when we have lots of ATP around and we're producing lots of nitric oxide, vessels will dilate and allow the blood to pick up the ATP and take it to where it needs to go. Now, mitochondrial anatomy is quite interesting here. So we have basically the outer layer, so the cell membrane of the mitochondria is here. And then we have the cytoplasm inside the mitochondria is here. And then we have this outer membrane and an inner membrane inside the mitochondria. So we have the cell membrane, which is basically surrounding the outside of the mitochondria. Sorry, the cell membrane is the membrane or surrounding the cell that contains the mitochondria. And then the outer membrane of the mitochondria is a separate membrane from this one. And then the inner membrane of the mitochondria is also another separate membrane. And between the two, we have this cytoplasm, which is really highly concentrated with a variety of different ions. Okay, mostly calcium, but other ions also. Now, so what happens is the basically the cytochrome C picks up the light that's coming in, and it causes activation, which allows calcium to be released and interact in this cytochrome chain. So this is where ATP is produced in this inner membrane of the mitochondria. And then that ATP will be shipped out of the mitochondria into the cell, where it can be used to do different functions. Now, LLT, low level light therapy, has been used in a lot of different therapies or therapeutic applications. So we can use it to reduce inflammation of joints. We can use it to reduce edema surrounding joints, chronic joint pain, healing of wounds, and we can also now, more recently, use it to treat nerve issues and brain problems. Now, these are sort of a rough compilation or summary of what some of the effects of laser that we know can do. So we know that we can produce an analgesic effect. We know that we can produce pain relieving effect. We know we can produce microstimulation, and that's through the release of nitric oxide, increased lymphatic flow, which we'll talk about, accelerated wound healing, stimulation of cell metabolism, acceleration of tissue regeneration, and that tissue regeneration can also include neurological regeneration, neurological functional activity. Okay, so a lot of stuff happening when we put light into a tissue. And so what we'll do now is I'll just take a break because this one's getting a bit long, and we'll start with the second installment of our laser series. So stay with us. Go to the YouTube channel and just go to the next Laser 2 video, and we'll continue. Just before we go, I'd like to remind you to subscribe to the channel if you like if you like the content. Subscribe to the channel, like the information, so that the algorithm knows that people are watching this, and it will send us out to more people. And I also will include in the comments section the link to Alex Fergus's website or YouTube channel, where you can see actually the full 2 interviews that we've done so far. I think there's a lot of information there. All right, so I'll see you in episode 2 of the Laser series.